Hello. Yeah. Okay. You would have seen me running around. I work at Gojek, so that's what I help organize this. So, yeah. So today I'll be talking about database reliability. It's a bit different. It's not the conventional Python related Python core Python stuff, which we really talk about at BangPypers. But why I chose BangPypers for this was that because Patroni, which helped us improve the database reliability at Gojek, is written in Python. So I'll do a deep dive into how it works and everything. So let's go into it. A bit about me. Yeah. So I have been working at Gojek for the past 4 years. I've been helping building the developer platforms and the cloud platforms. Currently, I'm working with a database as a service team, which is, yeah, we take care of managing and abstracting out all the databases like Patroni clusters, PostgreSQL, Redis clusters, Sentinels, Elasticsearch, MongoDB, all that stuff to the developers so that developers don't have to worry about that. They just can do 2-3 clicks and the databases are up and they don't need to worry about anything at all. So that is what I have been doing for the past year or so. When I'm not working, I make music, I play guitar, and I sing for a while, and I work out at my home. I have a home gym. So yeah, I'll talk about the agenda. First, I'll set context on how much the scale is, right? To understand how much the databases affect the systems, you need to understand how much scale you're working with, and what is the microservices architecture we are following, and how much it's important, right? So, and then we will discuss how the databases and reliability come into picture, so that just to build a plot why it's important and how we can solve it, what are the problems we are facing, and how we get to solve it with Patroni. And we will talk a bit about Patroni, how it is, what it is, what goes behind the scenes, what helps, what makes the Postgres normal databases systems highly available with the help of PostgreSQL, and sorry, with the help of Patroni, and increasing the availability of the systems. Apart from that, we'll do a deep dive into Patroni, how it works behind the scenes, what are the workflows which are present, what are the loops which are present, and how it observes the PostgreSQL process and makes sure that it's highly available all the time. A few more things I'll talk about at the end is that I'll share the lessons and experiences from managing Patroni clusters on production for a country level scale for Gojek. So that's what I presented as well. Yeah. So just to set a bit of a scale, we have around like, I don't know how many teams, so many teams, and we are around 600-700 microservices, and like each of them have, when I'm talking about databases, I'm talking strictly about PostgreSQL here. So around 400 or so have databases in them. So they are around, all the microservices are talking to each other. It's a intertwined architecture in which most of the microservices are connecting to each other and are dependent on them. So like you can think about, I'll give a brief intro on what Gojek is, because a lot of people might not be aware. So Gojek is a super app platform in the Southeast Asia. So you would see Zomato, Swiggy here in India, Uber, Ola, Porter, and everything, right? Swiggy, Instamart. It's all of those apps in one app. So it's like a super app with all of these different utilities and everything in one single app, right? So that's what the main part is, just because there are so many diverse use cases. We need to make sure that all the microservices are talking to each other. Like there will be one microservices for just the profiles, for the user profiles, one microservice for allocating the drivers to their jobs, to their bookings, basically. One for food, one for transport, one for logistics, and could be so many. So there are multiple teams for that as well. And our job to maintain the reliability of the databases is to maintain the reliability of all the databases. I'll talk about that as well. Yeah, so the point is that it's a bit difficult to pin down the scale of the databases we are dealing with when you have so many microservices, right? So we would talk about one of the service, which is the allocation service, in which assigns the bookings to the drivers, because most of our core workflow, which is transport, like booking a cab, getting an order, food order, like any grocery order or whatever, could be boiled down to the allocation service, which allocates the driver to the bookings, right? So we will take a look at the scale of the database. This is just the queries per second on the PostgreSQL database of the allocation service, which is around like 600K requests per minute, and it generates around 12,000 walls per hour. So walls is the write-ahead logs. It is just basically a transaction log, and it generates around five walls, which are size 16 MBs each per second, which is a lot of volume. If you have not been working with databases, you will tell that if a normal database would generate around like 15, 20, 100 walls in a day, that's also going to be high volume, but this is ultra volume. This is the largest volume I have ever seen. So that's scale we've been working on. Apart from that, for that same database, you will have like 18, 80, 19 billion inserts per month and around 100 billion in fetches. So that requires the database to be up. If the database goes down, then your entire Gojek workflow goes down. And you cannot avoid that because that will incur extreme business losses. So the reliability is extremely important. Mike, the question is that will a conventional PostgreSQL system be able to handle such a load? I'm too forward. I think, yeah. Am I? Yeah. Good. Yeah. So the thing is that will a conventional PostgreSQL system, like just a master slave system, which we have, right? Because Gojek has worked from the ground up, and the thing is that we believe in a normal application in PostgreSQL, which will scale. This is not a comment on how PostgreSQL itself would scale on a country level, but a question on the architecture of it. Let's say if one of the VM goes down, what happens? So that's the question. Will it be able to support a country level scale? So let's discuss a few cases why it won't, and what are the challenges which anyone could face facing such a scale on that level. Is that let's see a very normal application database system where your API traffic is coming from a load balancer to the application server. It could be a Django app, it could be a Flask app, it could be a Rails app, and it's talking to the master database, and master database is replicating to the replicas. So just one master, two asynchronous replicas or synchronous replicas. Let's say there's two asynchronous replicas which are streaming the write-ahead logs or the walls to the replicas from the master. Everything goes well. What happens is if the DB goes down, if the master goes down at this current moment, I will explain why it goes down. So if the master goes down at any level, any point of time, what would happen is the app would go down, right? And the replication would stop, but that would still mean that the data is still present in one of those replicas. If the data is present, you can redeploy your application, point to the new database, promote it as a master. That will take 30 minutes. 30 minutes is a huge time. You would have 50 people on the call, and everyone would be on your heads that what's happening here. So that's a very stressful situation. No one would want that to happen, right? And we all use cloud providers, and this is bound to happen because we are using VMs. You are aware that it's not a whole complete bare metal system that you would be able to not be able to escape from the noise neighbors problem, or like from the other systems in the data center. So like one of the cloud providers, I won't name the cloud provider because I don't want to, provides the uptime for a normal compute for around 99.9%, which is around 8 hours, which it guarantees a less downtime than 8 hours, 40 minutes, 1 minute, which is a lot of time. But the point is that in the architecture before, we had created the replicas in different zones, so which is still around 52 minutes of downtime per year. That's the level at which the SLA of the cloud provider is. So this is the max, this is the minimum, this is the max they will go to. If you go beyond this, they will give you some financial credits and everything, but that doesn't incur the losses you would face, right? So we need to get out of this, because it might be that around from 0 to 52 minutes of downtime, your application could go down, right? So even an hour of downtime in 1 year is a huge loss for the company. So how would you can correlate by this that the application downtime is approximately equal to the database downtime, because the database goes down, the app goes down. Yeah. So what we wanted is that a target of a around 5 nines of uptime, less than 5 minutes of downtime, which is very much achievable with today's systems. But as you scale up from the ground up, you have just one PostgreSQL node running, serving all the traffic. This is a bit daunting. So yeah, let's discuss how and why this is important. So before that, I'll discuss a few more cases why the conventional PostgreSQL system does not scale up for a country level scale. This is a scenario where the DB would have gone down. You would have deployed your app to point to the new master. You would have promote a replica, make it a new master, and point your application to the new master. What happens is that you would not know at any point of time, there might be a possibility in the incident call that one of those applications or one of those workloads were pointing to the old master as well. So this causes a split brain scenario. A split brain scenario is when two instances of the same database split and they diverge from their own timelines. So the red master would be on a different timeline. The green master would be on a different timeline. So after the host error had happened on one of the nodes earlier, it would have restarted and had become a master again. So which you have two masters for the same cluster. That is a very common thing which has happened, and it's a pain to debug this. It's horrible. So I remember that we had a very high throughput system and this happened. And we had to debug it and then figure out what data is where, and then pick out the data which was in the old master and pick it back to the new master, which is very difficult in PostgreSQL because for less throughput system, it's all right. For high throughput system, is a pain. And your database becomes irrecoverable and your data becomes inconsistent to a point where there's no coming back. So this messes up the whole database and you have to then restore from your backup and everything. So that takes a lot of time, right? And the point is that the actual business loss to this would be that might be that you're ordering something. The order is gone. Where is the order? You would then that causes a lot of bad reviews. So everything is related, right? One half an hour of downtime would cause like 100,000 one-star reviews on your app, which is the actual metric people are tracking, right? So that is something how the database reliability goes down to the application success, to the business success as well. One more thing, I'll just point out to the issue with the normal conventional system is that you would have created a new master and there's no concept of a global configuration in PostgreSQL. Let's say you have 3-4 nodes in a cluster, you can define the shared buffers like, so she was talking about the first talk he was talking about the buffers. So the thing that is that you need to make sure the buffers are suited to the traffic. Normal recommendation is that the buffers should be around 25% of the RAM and the cache should be around 50% of the RAM. But if that's not the case, your database performance will go down. So latency will increase and your orders will take more time. So in this case, what would happen is that in case of a misconfigured, newly promoted master, your application will start to increase the latency and your orders will start to increase. So that's not the case. That's the thing is that allocation service or whatever service is being called by multiple order management systems, right? The order management systems will start to time out, drivers will not be allocated, orders will be failing, and everything goes down, right? So that's a thing which comes in the picture as well. And that's the point to make sure that this is not the case. You need to make sure is that too much manual process to make sure that the configuration is same everywhere, and it's just a lot of pain. It's okay to do it on one cluster. You have a question? Yeah. This is not the, yeah, that could be one of the things, but in a cloud system, what happens is that one of the nodes will randomly go down. I explained earlier that if it would give you a 99.99% of uptime, which means that it can go down for 50 minutes in a whole year, right? Go down, the VM goes down. The VM itself goes down. Not the data, it's not a question on the database going down, the VM itself goes down. If the VM itself goes down, the process goes down, right? Then the database would become unresponsive. So that is the thing. Apart from that, that can also be the case when the DB gets too cluttered up and too heavy load that it gets restarted. That's also is a good possibility. That happens. So in that case as well, you would need a beefed up box, a beefed up replica to fail over to. I'll explain that later as well. No, no. There would be only one master at a point. In relational databases, in normal MongoDB or column-based databases, you could have multiple masters, like Redis could have multiple masters. But PostgreSQL, you would want only one master. Because I explained earlier, you would not want two masters and diverge from the timeline. That's very important for the integrity of the data. So you would have one master. I'll just go back to this. Yeah. Yeah. So you will see that it's all the apps are writing in one node, and that node is replicating the data to all the replicas. So that master node is responsible for replicating the data to all the nodes, not the application writing to both the replica as well as the master as well. Yes. Master is the source node. That's correct. With distributed systems, now it's leader. Now we call it leader replica. Master slave used to be an earlier thing, but now it's all leader replica and everything. So for all these questions, there are a few more things which we'll discuss about why PostgreSQL is not that good of an option. PostgreSQL itself as an entity is amazing to scale. We have had a lot of services written for PostgreSQL that scales very well. But the system behind which how it's architected, that's the problem. So that's where we'll discuss how Patroni solves it. Patroni is an open source repo, open source library written in Python, and it's actively maintained by Zalando, which is a European, I think, fashion brand. So they maintain that library for a long time, and we have worked on contributing a few things on that as well. Apart from that, it converts Postgres system into highly available, gives you 5-6 nines of uptime, and then makes it fault tolerant so that you would not face the issue like I described before. Make it disaster ready in case one of the zones go down. Let's say there are three data centers in Taiwan. So if one of the whole zone goes down, there was an incident in Paris, I think, an year ago, when the data center was flooded and the whole data center went down because all your data went down. There was an issue with the GCP region. The whole region went down. So you would not be able to recover from that, right? So that is also something we need to take in mind, and how Patroni helps with that as well. I'll explain how. So this is, I think, is it clear to see from there? The small text might be a bit blurry, right? Okay, I'll explain it, no worries. So this is how a normal Patroni cluster with an application interaction looks like. It's similar to it. You would have a load balancer in front of the three nodes. Earlier, you would have reader, replica, and master. Now you still have a reader, replica, and master, but there would be a load balancer in front of it. And the Patroni agent would be running on each of the nodes. So for each one of the nodes, Patroni would manage and observe the PostgreSQL process. So it's like a controller over the PostgreSQL process and manages and observes its behavior. In case if it goes down, Patroni acts upon it, and it has REST APIs. So that for the load balancer to know that which is the leader at the current point. Let's say the leader is the red one. It would give a 200 for the slash leader API, and the others would give slash 200 for a slash read or slash async API, whatever. So the point is that the load balancer would know at any point of time which is the master. So in case of a failover, I'll explain how the failover process works as well. The load balancer would know where to point, and it would point to the leader as well. So here's one more thing, is that there's a concept of leader election in distributed services, because you would want to have the leader to the running PostgreSQL process at any point of time. So that is where the distributed consensus comes in, and it takes care of electing the leader in case of your leader going down. So I'll explain the high level flow as well. So yeah. This is a distributed consensus store. So it takes care of keeping sync of your process, knowing that which of the process is up. So let's say if your leader, I'll explain that in detail here, is if your process leader process goes down, right? DCS is responsible. DCS here in reference is console. We have been using console for DCS. So DCS itself would be responsible for knowing which is the leader, which is the replica, and which is the other nodes, basically. So in case of node going down, let's say the PostgreSQL, the leader node went down, right? What would happen is high level, this process looks like this. The DCS would tell that I am not working anymore. Patroni will tell the DCS that I'm not working anymore. Please do something. And the DCS will ask the main DCS cluster to remove the leader lock, that remove the leader lock for this particular cluster on the leader node, which has gone down. Now the DCS cluster will trigger a leader election, and it will start a leader election on the remaining candidates, which are the replicas. In that sense, what the next thing would happen via a set of steps, which I'll explain later in very detail, is that it chooses a new leader, and the right traffic will start flowing to the new leader. So that this process takes around less than 1 second. So if the leader went down, the load balancer would know immediately that it has went down and start routing the traffic to the new leader. So this earlier mean time to repair, which is the common metric we use to mention how much time it took to repair, which is commonly mentioned in RCS as well. So that is now reduced from earlier around 30, 40 minutes. So manual intervention, some would come call and some would come down to the call and everything and fix it. It's now less than a second. So this is how Patroni works with the help of leader. Yeah. Yes. Yes. So DCS also has the same problem. The thing here is that DCS also has a master leader and multiple followers. So like console, we would provision a console node with 1 leader and 5 followers. So that in case the leader went down, the follower would become the leader. So that same thing is being transferred to the DCS cluster as well. That same principle of automatic failover. So this process itself would be called as an automatic failover. Earlier, the failover would have been done by promoting manually promoting the replica to the master and everything. So this is how it takes place. Yeah. Yes. 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 So what happens, I'll show the whole flow, how it works, but when the fail leader comes back up again, it will join the cluster as a replica. It will sync back with the original leader that how much data have I missed in terms of the write ahead logs, and it will join the cluster back as a replica. So that's what it is. The status of the cluster and everything, how the configuration should be, is stored in the DCS itself. You can consider DCS as a key store as well. So the next thing is that what Patroni solves is that it allows you to maintain global configuration. Let's say I wanted to update my shared buffers to 2 GB or whatever. What it would do is that the Patroni would take care of the updation, apply it on the PostgreSQL process, and relay that information back to the DCS, so that DCS know that all the cluster needs to be applied that new configuration. Because DCS is the only source of truth here. We would not touch the DCS at all. And that knows what is the configuration which is being running on the leader replica and other replica, right? So sometimes people would go ahead and drift from the actual configuration, which is in the DCS, which is source of truth. That causes a lot of issues. So the best way is to make sure that you always go via the DCS route and make sure that it is always same. The configuration is always same on the PostgreSQL process, which is on the DCS as well. So similarly, what would happen is that it would be applied to all the nodes, and it would be prompted to the user to maybe reload or restart the PG process. Patroni would itself take care of knowing that which of the configurations which requires a reload, which of the configuration requires a restart. If it requires a restart, it will give you an alert that do a pending restart or something. Reload, it will do manually, automatically. So just a few things about Patroni. It's almost instantaneous. You would not even, like people who have been working with Kubernetes, right? You would see that whenever you do a rolling upgrade, it takes take the old nodes down and spin up the new nodes, right? It's almost instantaneous, and the traffic does not flow that well. So that's a similar process in this as well. Whenever we are doing maintenance or something on a Patroni cluster, we'll upgrade the lead replicas, then we'll upgrade the leader. So similar to a rolling upgrade. And that failover helps us in that cases as well. So that's a planned failover. The case I was mentioning earlier was an unplanned failover. It's way cheaper than running managed TV stores. A lot of people would be running RDS or anything, and it says that it's going to be available. It is definitely, but it's expensive. And when you are running that scale, expenses matter a lot. And now the sentiment is also is that you need to make sure that the money stays within, right? You don't spend a lot of money on cloud. So cheaper solutions which run better are a more favorable option. Cluster management is much easier because I explained earlier, Patroni gives you a REST API so that you can know which of the node is leader at any point, which of the node is replica at any point. I want to do a switch over, I want to do a failover. I can do everything via APIs. So I can write clients over that API and expose them on any interface like a CLI or like a web interface. So that makes life easier for the database management team to handle it, for the application team to handle it. So that our goal is to abstract all that out for the application owner. So that application owner clicks one thing and you perform a rolling upgrade, or you perform a failover, you perform a scale up, or whatever. There's one more thing is that it also supports multi-region deployments. It's like as I said earlier, that one of the regions would go down. You would want that your database is present in one or more regions, like Taiwan, Singapore, Indonesia. It should be present in all. So I'll discuss that as well. So this just I don't know if I should mention GCP here, but let's go. uh, uh, it says that AlloyDB is similar to RDS on GCP. It says that it costs around $1,000 per month. But if I would run a 2 DB Patroni cluster, it would cost me, with the same configurations, almost the same configurations, it would cost me almost half with disks and everything included. So it costs me around half of that. And imagine that we have 500 clusters. So we have N1 standard 4, or like, I'm not sure what the AWS equivalent is. Those are 4 core boxes. We have 64 core boxes, 32 core boxes. The one I was mentioning earlier was the allocation service that has 64 core box. And the difference increases exponentially when you have bigger VMs present. So that's one thing that is cheaper, definitely. So now yeah. Yes. About management overheads, like database, anything else that the managed database is providing, those things will still count. Yes, definitely. So that's one thing that automatic upgrades. I want to, there's a new version of Postgres coming in. I want to upgrade it. There's a bug fix patch going on, like a security vulnerability, but don't even take care of that. Even as that if the so in terms of RDS, if there is more elastic storage that needs to be added, take care of that. So I think you have to, that's what the thing is, that you have to build tooling on top of it. It allows you the interfaces, but you need to build tooling on top of it. It allows you to create, perform version upgrades. It's possible to do a logical replication. I won't explain this because that's a bit too into Postgres. But you can do logical replication globally to upgrade to a different node. But that's a manual job. That's what the thing is, that it offers. It's less expensive, but it comes at a few maintenance things which the DBT, which we basically do. That's that we automate and we ensure that those are streamlined. Version upgrades, scale ups, like whenever someone's CPU is hitting 80%, we just run a few steps and it becomes scaled up. We have written processes around Patroni itself that it can be done. So I'll just do a brief about how Patroni works, like very brief, the one before was very high level. This would be very deep into how it works. So whenever the Patroni process starts, it starts the, okay, let me go into this. This was a, is it visible? Can you see it? It's a bit blurry, right? expand it. Visible? The text is a bit smaller. I had generated this graph from GraphViz. It did not allow me to do it better resolution than this. Are you able to see? Right? So what happens whenever the hello? Yeah. What happens whenever the Patroni process starts up is that it starts the DCS, initializes the console, which is the DCS here, initializes the PostgreSQL process, and then initializes the REST API and make sure that everything is placed. But I'll explain how the process looks like. It initializes the HA loop. So like it's a loop which is running every X seconds, like 1 second or less than 1 second, and it's syncing the state of the current cluster with the DCS. Yeah, so it's syncing the current state of the cluster with the DCS at every point of time, and this is this loop which runs every very smaller interval to make sure what is the status of the cluster. So if it's whenever you start a cluster, not new cluster, let's say, it would load the cluster from the DCS. If it's a new node, it will add that node in the DCS configuration, and then if it's not, then it will just check if it's working, if it's starting or not. And so it will also check a few things about if the cluster was failed earlier, if it's not, if it was not working, it will remove the leader lock and say that you're not the leader anymore, and we'll start the leader election again. It will also check if the data folder is empty. Let's say there's already some data on the Postgres cluster, it will go ahead, and then if it's not, then it will start the bootstrapping process, which I discussed in the later stage in the next slide. And then it would initialize the cluster, check if it has a leader or not. If it doesn't have, then it will initialize the new cluster and add it into DCS. If it has, then it will check that the node, if the Postgres process is healthy or not, and then check if the cluster has a leader or not, because the leader is being checked by the leader lock. The leader lock is continuously updated on the DCS. That is being checked, and then it checks in the if the Patroni process cluster is unhealthy, it will check. It will go ahead and mark that current node, which if it's healthy, as the healthiest node. If it's not, then it will try to follow another leader, and it will if it wins the leader race, which is done by the consensus raft algorithm. I would not go into explaining it because it will take around how much time? Okay, I'll take five minutes. Yeah, that's almost most of it, how the process looks like. Yeah, this is the node bootstrap process, which is very similar to that. I will share this as well. One more interesting thing in the Patroni is that you were mentioning is that what happens in case the console goes down, if the DCS goes down. Patroni implemented a very special thing is that it turns on pure raft as well. You would just need to raft is the raft consistency algorithm, so it has a Python implementation of raft working on itself as well. So you can rely on not using any DCS at all, and you can use the PySync obj library to make sure that this particular data is being replicated to all the nodes. So it initializes with the sync obj class, and then you need to define what are the addresses where you need to replicate that data. And whatever action you want to do, you can use the replicated decorator over that. So it uses that itself to manage the routing as well, to remove the dependency on the DCS. So I just asked ChatGPT that if in case you would, in a normal cluster, what would happen is that let's say there are 3 nodes of a cluster, and any one of them needs to be up for the whole cluster to be up. So like if 2 of them goes down and 1 is up, the cluster is up. The uptime would be calculated by that formula, which is taken from a reliability engineering journal, and it comes down to almost, I don't know how many lines are those, but ideally that is the thing, that it will come down to very less than a second, but it's not practical. I'll explain why it's not practical, because the replication, everything takes time. If there's a very high throughput thing, Patroni will make sure that the replication takes time and the replication will complete, and then only the failover happens because there's no loss in the data. That takes a few seconds, but that's still less than 52 minutes. If a normal running cluster is there without maintenance operations, for unplanned downtime, it would be less than 5 seconds in the whole year, which is almost 5 minutes of time. I'll just cut short to this, what we are running right now. We have currently around 200 plus clusters on production, and we are running almost 60 TB of data in and out every day. And we guarantee around, like, our backup strategy guarantees around like 10 MBs of data loss. If less than that, in case of a worst case scenario, like that region goes down. And we use console GCs, and we do have ISC. I will not go into this. This is the graph which looks like that, how much data we get in. This is the tunnel graph. This is the visualization of the tunnel, how much bytes we get per day. So this looks like weird, but that's what around 60 TB looks like. One more thing is that I was talking about multi-region. This is similar to multi-region, is that, you can have the nodes DCS cluster in each of the, in each of the region, and you can use console to redirect your reads and writes to wherever you want to. And this is how we make sure that less than 10 MB of data loss is there, because we are shipping the walls which are generated every 10 MBs of data to a cloud storage. And we have written a logic by which we could generate the walls, and we could fetch the walls back whenever you want to boost up the cluster with it, which guarantees almost less than 10 MBs of loss, which we have calculated earlier as well. Yep, that's it. Have any questions? Yeah. Yeah. So there were a few more extensions, like we went the managed solution route, but that was costing a lot. Cloud SQL basically, but that was costing us a lot, and that's why we came back to a managed solution. There were a few downsides. We used a few extensions called Citus. There's a Citus extension. We use that as well, but that is also not serving us, because that's a bit.
It will be supported by Patroni as well, right?
Citus. Yeah, it will. Now it is. Earlier it was. I'm not sure when we were doing it at that time, but now it is supported. So we did a few checks before, but this is what we came back to. Mostly few extensions. There was a Postgres operator which we checked, and there was a Percona system which we checked. But this was the easiest, and this was the most open source, so we could figure out what's going on here. Yeah.
How did you decide that, like, shifting is not going to, I think kind of people say, how do you know that it's going to work, right? Because you shifted to this one, but how do you know whether it's going to work or not? You did put in some time for monitor and all of them and looked at it? Or
what we did is that we did a POC, basically. We checked how it will go. We put it under extreme load, and we did failovers under that extreme load. Like we simulated load via JMeter scripts to make sure that how much load is actual load of production is coming, and then we did failovers to see how much data is being lost, how much traffic is how much packets are being getting lost in the 1-2 seconds of failover, how much time it's taking. And then we came to a conclusion that this is probably a solution which will work. And then we experimented into some systems as well.
This is by no means just a 40-minute talk. Okay, this deserves a full session of its own.
Yeah, definitely.
But is there an engineering blog that you guys have on this migration?
No. We are planning to write it, so okay. It's just to start. There's so many things to talk about. I just ran out of time.
Exactly. So you ran out of time. So you ran through the last bit, which is fairly impressive work, right? So would have liked to learn more. So
yeah, we would write a blog on this. Yeah.
Thank you.
Any questions?
Approximately how much time did it take you to settle on this problem needed to be solved and implementing it finally?
So it started around 2019, 2018 that we're actually facing this issue. And from 2020, a few people, I was not part of that team, but few people started doing the POC, that this needs to be done and how the POC would look like. That took around 6 months to do the POC, to do actual testing. And then we started, a few other teams started building it from the ground up. And then we had like around 50, 60 clusters at that point. And then we took all the tooling, went back into one team as a consolidated team. And then now we are around like 400, 500 clusters strong. So that whole process took around like 3 years or so. Yeah.
Thanks a lot, Abhijit, for the talk. Next, we have Abhiram.